So we're wrapping up our coverage of parallel streams. I'm going to have just a few more videos on streams and parallel streams. Then we're going to talk about computable futures right after that. But let's talk about when to use Java parallel streams. So here's a quick synopsis of when you should use them. You should use them when the behaviors that you have are independent, they are computationally expensive, they're applied to many elements of data sources, and also when multiple cores are available. That's kind of a quick synopsis. Let's break that down and take a look at it in more detail. First thing to remember, and this is a question that often shows up on quizzes, a parallel program always does more work than a non-parallel program. And work in this context means extra steps. What does it need to do that's extra? Well, it needs to partition the overall tasks up into subtasks by splitting things up, as you can see here. It then needs to process all the subtasks. That's going to happen whether it's parallel or sequential. So that's typically all that a sequential program does, because it doesn't need to break things up and partition them initially. And then finally, it needs to combine all the results together, the sub-results back together into the final reduced result. So operation, or step 1 and step 3, are extra relative to what a sequential program does. So clearly, if there's not some win that comes from other factors, then we've got extra overhead by using parallel computing. Now, the thing to remember is that the parallel streams framework is trivially easy to parallelize, but whether it's going to actually be a good idea to do that is another story. So you have to think through carefully when you would use it and when you wouldn't. And there's some guidelines you can see here at my friend Doug Lee's website, giving some guidance based on the experiences they had when they built the framework. So there's certain conditions under which Java parallel streams work. And there's a wonderful quote by Oscar Wilde that no object is so beautiful that under certain conditions it will not look ugly. I'm not sure exactly if that's always true, but that's a good quote that goes in here. I'm not sure that this particular beautiful tree would ever look ugly, but that's another story. So what are some of those characteristics? One is that the tasks are independent, or as we like to say, embarrassingly parallel. As you recall, embarrassingly parallel tasks have no dependencies, or very little, but usually no dependencies between them, and there's no need to communicate at all as they run. Good example would be searching for phrases in a list of input strings. So we've got all the works of Shakespeare. We want to look up the works of phrases in the works of Shakespeare. That's a wonderfully embarrassingly parallel processing task. Downloading a bunch of images and doing image processing and storing and displaying them, as we do with our assignment. Another good example of embarrassingly parallel tasks. And you can see some cool examples here in this Search Stream Gang application. We didn't really talk about that because it's more detail than I wanted to go into, but it's a good place to see lots of different examples and compare and contrast them in terms of which performance optimizations and which concurrency and parallelism models work the best. One of the cool examples, which we also will not look at in detail, although it's cool, I've got videos from previous classes that go into this. You can search each phrase in parallel, you can search each input string in parallel, and you can search chunks of each input string in parallel. So you can make things superly duperly aggressively parallel. And this is sometimes going to be a win, again, depending on other factors. So you can really go to town and parallelize things top to bottom, stem to stern. Another characteristic that gives you motivation to use parallel processing and parallel streams is when the processing is computationally expensive. So if each behavior takes a long time to run. And of course, if you have lots of elements to apply to. So the best situation is when these sources can be split evenly and efficiently. If you recall, we talked about situations where we had an array list versus a linked list, and you saw as n got large, the array list was faster than the linked list. And we have this wonderful n times q model where n is the number of data elements to process per thread, and q quantifies how intensive the CPU processing is per element. So the higher n and the higher q, the more ideal. The lower the n, the lower q, the less ideal. Once again, searching for the phrases in the works of Shakespeare, that's a pretty good one. If you run it, you'll see that the embarrassingly parallel nature makes it work very well for pretty much all the various concurrency and parallelism models that are part of the Stream Gang example. And of course, the other case where it matters to do things in parallel is if you have multiple cores. You can use a single core, but you're unlikely to get much of a speed up unless you have certain factors like you're using a chip that has one core but direct memory access, so you can have I/O running in parallel with the chip. Most, if not all, modern processors are multi-core unless you're dealing with super duper embedded systems, in which case we're probably not running Java on them anyway. So under the right conditions, like we just talked about, parallel streams can scale up very nicely on multi-core and many-core processors. There's an example, which again we didn't really look at, where we can see that the most aggressive parallelism model performs much better than the sequential models, and that's not surprising. So there's a couple other things to talk about next, but this is when you should use parallel streams. Next, we're going to talk about when you should not use parallel streams.